on our calculators here, I would like for us to graph this function. Now, we have done a lot of our graphing via Desmos, so some of us may not know how to graph on this graphing calculator I'm showing you today. On your graphing calculator, you press y equals. It's a it's a gray button towards the top in the graphing section. It gives you a screen. This kind of looks like the Desmos screen where you would type stuff in. However, you can only type in functions that are set equal to y. So we are going to have y equal to x squared plus 3 plus 5. We're going to type that in. Now, how do you get the x, you might ask? This button right here next to alpha, do you see how it says x, t, theta, n? If you press that, it types an x on your screen. The graphing screen is the only place you should be typing in x. Do not type an x on the home screen. That's different. Then we're going to square it. There's a square button right here. Square. Then we do plus 3. Plus 3, and then another x. So I press the x button again. And then plus 5. I'll give you 1 second to get caught up with me. Once we've got it graphed or typed in, we want to graph it. There's like legitimately a button that says graph, so you're going to press that. This is how it shows up on the screen. So I'm gonna sketch it on this video for those of you who don't have a calculator. It looks something like this, am I right? Those of you who have made it to the lesson that talks about solving by graphing, we look for, and honestly we learned this in Algebra 1, we look for the solutions to an equation here along my x-axis. Is there any place where that graph crosses the x-axis? No, so how would you answer this question if I said, what are the solutions? You'd say, no, technically you're supposed to be saying no real solutions. I've been accepting no solution for a while because we didn't use what are called complex numbers, but we've been specifically supposed to be saying no real solution because what's cool is that there actually is a solution to this quadratic. We can't see it because it doesn't happen in real life. This is where real life is along the x-axis. So if it's not going to be real, what do you think you're going to call it? Deceiving. How about a different word for the opposite of real?
Fake.
Fake? Can I give one that starts with an I?
Inconclusive.
No. No, that's a different thing. That's cool. These are good ideas. Opposite of real that starts with I. Think like the opposite of real is imaginary. So fake. Yeah, we are going to be working with the imaginary number system because that's legitimately a thing. There are real numbers, which is what you've used for math for like your whole life so far, and there are imaginary numbers that we're going to learn about today. Like legitimately, they're called imaginary numbers. Okay, so before today, we'd stop right here on this problem and be like, there's no real solution, move on. Today, I'm going to help you figure out how to actually solve a question like this. It's going to be cool. Okay, now what these are called in a large part is called a complex number. It's called a complex number, and it looks like this. So you might want to like bubble this right here. A plus or minus bi. The a part right here, the number without the letter I next to it, is a real number. That's the stuff we've been dealing with since forever. The second part of this, where it says plus or minus bi, you see how there's an I next to that number? The I stands for imaginary. So that section of a complex number is called an imaginary number. So a complex number combines a real and an imaginary number. So when you're writing an imaginary number, you're going to put a little I next to it. Now I recommend you writing your I's like they're written on this paper. What do you notice about the bottom of this I right here? Is it just a stick? No, it's a little curve, right? If you just drew a stick, you're going to be like, that's a 1, right? No, it's an I. So make it a little curvy I. That's a good mathematical technique right there. To make sure you know it's an I, give it a little tail. Okay. Now there are some properties of complex numbers that we are going to be using. Most importantly probably is these two properties right here. The imaginary number comes from the fact that when you take the square root of a negative number, the negative is going to pop out as an I. The negative is going to pop out as an I. Additionally, a property that will come in handy later is that if you are doing I squared, so I times I, all that's going to evaluate to is -1. So that's something for later. So you're just going to replace it with a -1. But most importantly right now, if you see that you have square root of a negative number, just the negative part whoop, pops out as an I. The rest of the numbers in that square root, you're going to treat like the lesson we had on square roots. So if we wanted to simplify square root of -45, first thing you do, because you notice there's a negative underneath the square root, underneath, not in front of, underneath, you're going to highlight it or circle it, and you're going to draw a little arrow, and popping out of it is going to be the letter I for imaginary numbers. We know this. That's the fact about imaginary numbers, that if you take the square root of a negative number, it's imaginary. Because you can't take the square root of a negative number. But after that, you're going to treat this just like we treated all of the other square roots from that lesson. Meaning, I'm going to try to break down 45 into a tree of factors. What's a number that's 45 is divisible by? 5. Okay, so it's 5 times 9, actually. Okay, can I break 5 down any further? Can I break 9 down any further? Yeah, 9 can break down to what? 3 times 3. Now, I personally, and I said this in this lesson too, I personally like crossing out the numbers that I've already made branches for so that I don't use them anymore. Okay. Let's think about what we did in that lesson. Those of you who got there, when you have a pair of numbers at the end of your branches, what should you do with them? Circle them and then put them on the outside. If you have a singleton, a number that's just by itself, has no partner, where do you put that number? Inside, which means when we reduce this square root or we simplify it, we're going to have an I in the front from the negative. We are going to have the 3 from the pair, and left over underneath the square root is going to be what number? 5. When we did this lesson on square roots, I had you multiply all of the things together, and you're probably like, Miss Quigley, you want me to multiply 3 times the letter I? Yes, here's how you do it. It's really complicated. That's a joke. It's not complicated. You do this, 3I. I times 3 is 3I. Just like we put the X letter second when we have like a variable, we are going to put the I second. That's just good mathematical notation. So boom, I'm done. I've simplified that square root. It's exactly like we did from the square root lesson. However, if it's negative, there's just going to be an I in the front of the square root. Simple, right? Okay, cool. Let's pause right here for a second. Problems on the inside of these. We can also do complex number arithmetic. Arithmetic is just add, subtract, multiply, divide. We're not going to divide today. We're just going to add, subtract, and multiply. But complex number arithmetic is very, very easy if you understand the concept of combining like terms. When I'm asking you to combine like terms, and let's say you have like 3x, don't write this down, just look. 3x plus 1 plus 5. How would you combine your like terms there? Which two things would you add together? The x's, the 5 and the 3 would be added together to make 8x. That's because it has like terms. Well, complex numbers essentially work the same. When you're adding or subtracting complex numbers, all you're going to do is combine the reals with the reals and the imaginary with the imaginary. What I mean by that is, do you notice in this first problem that -8 is a real number? And that -1 is a real number? And that 3i is an imaginary number because of the I. And -2i is an imaginary number because of the I, right? I combined the real with the real and the imaginary with the imaginary, which means I'm really doing -8 plus -1 and 3i plus -2i. Now, you can't do the I arithmetic in the calculator, but it's just like it was a variable. You can add the numbers together. So -8 plus -1 is -9. And then if I do 3i plus -2i, that's like 3 plus -2. It's just 1, right? So we're going to have 1i. There's an invisible 1 in front of that I, but we need to get used to not having it there in our final answer. So if in your work you need it, that's fine. I don't want the 1s in our final answers anymore. Now it can't be negative 9i. That's different. Negative 9 plus I. Make sure there's a plus sign there. So adding is simply combining like terms, CLT. Subtracting is almost simply combining like terms. But before we do the subtraction, we actually need to distribute the negative sign. That way we can combine like terms. So in the second example, we're going to CLT after we distribute this negative. So the very first thing you do when you notice that there's a negative here in the center, you draw your little arrows like this because we want to distribute that negative sign. We prefer doing addition at all times rather than subtraction. So we're going to make it an addition problem by distributing first. That means I end up with negative 5 plus 9i, no change in the first parentheses, and then negative 6. What's a negative times a negative? Positive. So I have positive 6. And then another negative times a negative, positive 6i. Once I've distributed that, do you see that we now have real and imaginary parts? Let's just combine our like terms. Negative 5 plus 6, that's 1. 9i plus 6i, that's 15i. I just combined my like terms. But so with subtracting, we had to do one extra step of that distribution. Addition, real easy. Just boop, boop, add them together. Subtraction, distribute, and then we can just add them simply together. Yes? I have 2 practice problems on the inside to check and make sure we understand this part. So open it up on the inside. We'll do the multiplication. On this problem this first one, this step that I showed right here is the work that I'm doing in my head. I really don't need to show this because I think I'm confusing you. If you notice, based on my color coding, the 2 things that are orange, I added together. Why? Because they were the same. The reason that I had it shown was I was showing that we were doing negative 8 and negative 1 close together. I didn't change any signs. But I was adding the real parts with the real parts and the imaginary parts with the imaginary parts. That step I showed in between was just to show you my thinking. If that confused you, erase it and just notice that we have the real and the imaginary together. Does that make more sense? I think I just confused everybody. My bad. Now this is a little bit more complicated than some of the things we've been doing. It is also potentially different from how you learned to multiply last year. When we were multiplying binomials in Algebra 1, you probably learned this Punnett square method. Do y'all remember this like Punnett square thing? Oh, yeah. Okay, great. If you remember how to use it, use it. I'm not showing that anymore. We're going to use a different method called FOIL. But if you struggle with FOIL, just know you can go back to that method with the Punnett squares. On your paper, I need you to write the letters F, O, I, L. FOIL is the order in which you will multiply the numbers in this binomial. The F stands for first. The first things in each parentheses you multiply together. It looks like this. Boop. I'm multiplying negative 1 times 15. The O stands for outer, which means I'm multiplying the 2 outside things. The outsides of this is negative 1 and negative I. You see how they're on the outside of the problem? So we had the first things in the parentheses, and we have the outside things in the parentheses. What do y'all think the I is going to stand for? Inner. So we're going to multiply the inside things together. And what do you think the L is going to stand for? The last. So we take the 2 last things in both the parentheses, and we multiply them together. So we're going to do it in that order. It's technically the same thing as the Punnett square, but it works faster in these problems to use the FOIL method as opposed to the Punnett square. And I know y'all like working faster. So we're going to do that first. Negative 1 times 15 is negative 15. If you don't trust me, you'll ask a calculator. We're going to go to the blue. The outsides would be negative 1 times negative I. Negative times negative is positive I. The insides is 9I times 15. What is 9 times 15? 135 I's. This is why I told you probably wanted a calculator today. And then we have positive 9I times negative I. That's going to end up being negative 9I squared. Whoa, where'd the square come from? There's two i's that I'm multiplying together, and when we had two x's that we multiplied together, we made it x squared. So we're going to make it I squared. Okay, pause. If I've lost you on this step, I want to find you before I keep going. Do we see where all of these numbers came from? What do you notice about the numbers in the center of this problem? They both have an I. Ah, so they're like terms. Can't I add imaginary terms together? Great, I'm going to do that. But at the same time, I want to do something else. At the top of this, well, y'all's is at the bottom, there's a second rule in the properties of complex numbers. It has a value for I squared. What does it say that I squared is equal to? Look at the bottom of your page. It's at the top of the correct notes, but it says I squared is equal to, so we're going to cross out I squared, and we're going to instead put negative 1. If you're like, where are you talking about, Miss Quigley? Here. I squared is equal to negative 1. So we're replacing I squared with a negative 1. That's what it says to do. Okay, we're going to do both of those things in one fell swoop. So we're doing 2 steps in one. The next line of my equation would say negative 15 plus 136I minus 9 times negative 1. Whoa, where'd the 136 come from? Yeah, 1 plus 135. I combined my like terms in the center and made one term out of them. Where'd this negative 1 come from? And where'd the I squared go? I squared is negative 1, so we can just like bloop, bloop, replace them. Well, isn't it just numbers now? What's negative 9 times negative 1? Positive 9. So really, this equation is like saying negative 15 plus 136I plus 9. Because negative 9 times negative 1 is positive 9. Last step. What do you notice here? With this number, negative 15, and this number, 9. They're like terms. Those are real numbers, right? They're not imaginary. They don't have an I anymore. I can add those together. We just learned that when we were adding complex numbers. So we're going to do negative 15 plus 9, which if you ask your calculator would be negative 6. This is why I highly recommend using a calculator. And once we have a real part and an imaginary part, no more square, no extra imaginary part, no extra real part, we're done.
Where did negative 6 come from?
I did negative 15 plus 9, the real parts right here. So I did this number plus this number, the real parts. Okay, let's go. We're going to take a second because I know later when you look back at your notes here, you're going to be like, I have no idea what happened. So we're going to put some words down next to this to talk about what happened each time. So you have steps. So the first step I did here that we can write down is I did the FOIL step. What did FOIL stand for again? First, outer, inner, last. Okay, so I did the FOIL, and then I did 2 things at once for the next step. I combined like terms in the center, and I replaced I squared with negative 1. That's 2 things. To make the third line, all I did was multiply the last thing. And my last step is to combine like terms one more time. So we really only have 4 lines to this problem. And every single one of them can be aided with the use of a calculator if you don't know your times tables. Or 15 times 9 is probably bigger than the times tables we have memorized. Okay, so we're going to stick with multiplying for the rest of today because it's probably the more difficult thing on today's notes. So go ahead and go to the inside. The numbers are a little bit all over the place. So look at in your notes for first period, it's question number 7 and 8, but mine are number 1 and 3. Again, I don't know what happened here. The numbers are wild. Okay, on numbers 7 and 8 for you, we have 6 square root of negative 121. We want to simplify this. The first thing I do, it's number 7. The first thing I do every time I want to simplify a square root is I look for these little negatives. Do you have a negative here? What is that going to pop out as? I. Okay, we take care of that first. Just get rid of the negative. Now I don't even have to think about it because it's an I in the front. I need to break down 121. 11 times 11. Can I break down 11 or 11 anymore? No, I can't. Those are called prime numbers. Okay, so I'm done breaking them down, and I'm going to circle pairs. And I'm going to put a little underline under singles. Are there any single numbers here? No, so I can go ahead and start simplifying this. I had the I in the front. I had a 6 from the original problem. Like, you see how there was already a 6 up there? I can't let that go away. I took out the number 11. Was there anything left inside the little house? The square root radical sign? Like, is there any number that I underlined? No, so if there's nothing here, then that square root is just going to disappear because there's nothing left underneath it. All we do here is 6 times 11 times I, well, 66I. Exactly. So we're just breaking down the number and then multiplying by the letter I. Okay. We're going to do this next example, but I want to let you guys give it a shot. Okay. This one has some leftovers in it, so I want to see what you can do with that. You're going to go ahead and break down the number negative 180 and see if you can simplify that radical. Okay, so on number 3, when you tried it, you may get a different tree branch than me, and that's fine, because at the very end, we're going to end up with the same numbers if we've done it correctly. So here's the first thing I see. I see that it's negative. What does that negative pop out as? I. Now, I want to be sure that you're using a lowercase I. That sounds super picky, but in mathematics, an uppercase I and a lowercase I technically mean something different. So please use a lowercase I. I saw that around the room. Another thing that we would break this down as, sorry, not another thing. I don't know why I said that. I'm going to personally break this down as 2 times 90. If you pick something else, don't erase. It's probably fine. I'm going to break this down as 2 times 45. I'm going to break this down as 5 times 9. And I'm going to break 9 down as 3 times 3. Do you see that? I went down the line as many times as I could until I have what are called prime numbers left. It's called the prime factorization of this number. What am I circling? Pairs or singles? A pair of 3s and a pair of 2s. Even if you did it differently, if you did your breakdown differently than me, maybe you started with 12 times 15 or 9 times 10, you should have ended up with the same thing. 18 times 10, you know what I mean. Okay, I have a singleton of the number 5. All of the circled numbers pop out, the single numbers stay in. So couples go out, singles stay in. Which means I would have an I, a 2, a 3, and a square root of what number? 5. Now, I don't leave my answer like this. I'm actually going to simplify that together and multiply the things. I times 2 times 3, that's 6I square root of 5. Okay, before we move on, because we're going to go to a different type of question after this, questions about this process, because some of us I know didn't quite get to the breakdown lesson with the square roots, but we're getting a crash course today. Are we okay? Are we okay to move on? So bottom line here, and I want to hear a chorus answer on this. If you were to have a negative number underneath a square root, what does it pop out as? I. Let's hear it again. What does it pop out as?
I.
Great. Awesome. Back to the front. Second. You're going to go ahead and do, it's numbers 2 and 4 on my problems. It's numbers 1 and 2 on yours for 1A. Okay, let's see this one together because I think we have some good questions. So if I'm doing a part that you had the question on, this is when you stop me. In problem number 2, I am adding these numbers together. Do I need to do any sort of distribution? With adding? We just need to add the real part with the real part and the imaginary part with the imaginary part. So if I was showing my work, which is where I confused everybody, I would be doing the 3 plus the negative 5 together, because those are the real parts. It's number 1 for you guys. Yeah, mine is out of order. And 4i plus negative 7i. Just the real part with the real part and the imaginary part with the imaginary part. You could probably do that step in your head. You don't have to show me that. But this is what I'm doing. This would mean I end up with negative 2 and then plus negative 3i, which I'm just going to write as minus 3i. If you wrote plus negative 3i, that's still technically correct. I would prefer one symbol, but it's not wrong. Why is it minus? Because 3 plus negative 5 is negative 2, and 4i plus negative 7i is negative 3i. I just put the real part and the imaginary part together to make my complex number. For your second problem, yours is number 2, mine's number 4. Remember, mine's out of order on this video. We know that it's subtraction. When we have a subtraction problem, the first thing you do is distribute. Distribute means multiply. It means change the sign of everything in that second parentheses to make it super simple. So we multiply. This would now be, and I'm gonna not do it in a color code yet. It would be the 4 minus 6i from the first one, and then change the sign of everything else. Minus 2 plus 4i. Now I have some real numbers, and I have some imaginary numbers. We combine the real with the real and the imaginary with the imaginary. That means this should be 4 minus 2, that's 2. Negative 6 plus 4, that's negative 2. So we do not do any sort of sign change on addition, and you change all the signs of the second complex number when you subtract. If you did not draw your arrows from the minus sign into that parentheses, I need you to do that. Okay. We're going to go back to the front for the last little piece of today. Your problems I think are number 3 and 4, but mine are number 5 and 6 right now. We are going to multiply, but this one's a little bit simpler. Do you see though there's only one imaginary number in front instead of 2? That means I don't have to FOIL, I just have to distribute when there's only one thing in front. So we're going to draw our arrows. Multiply. What is 5i times 4? 20i, because there's an I there. And then I'm going to do 5i times 7i. What's 5 times 7? 35. And what's I times I? I squared. Cool. Always we have to remember that I times I is I squared. Now, are there any like terms I can combine right now? Ooh, so 20 and 35, they have I and I squared next to them. Are those exactly the same? No, we can't combine them if they have the exact same letter and power. But we do have a fun fact about the number I squared. What is I squared equal to? Negative 1. So can't I just replace that with a negative 1? Great, I'm going to do that. This would say 20i plus 35 times negative 1. Well, guys, what's 35 times negative 1? Negative 35. So we would have negative 35 plus 20i. I I can see a question already forming in your head. Miss Quigley, why did you write the 35 first? It's a good question. For complex numbers, we always put the real part first. So do you see how, and the imaginary part last? Yeah, so you see how that's the real part because it doesn't have an I? And that this is the imaginary part because it has an I attached to it? We always want to put the real thing first and imaginary thing second. Let's see if we understood this simpler version before we start getting into the crazy FOIL stuff. You guys have it's number 4 for you, but number 6 for me. I want you to try that one. I'm going to give you only 1 minute because you don't need that much time. So we have a number in front of a parenthesis. That's our indicator that we are multiplying through distribution. So we should do this twice. Negative 2i times 3 is negative 6i.
Negative 2 times 4i equals negative 8.
Positive 8i squared. Negative times negative is positive. But then we have this fact about I squared. What can I replace I squared with? Negative 1. I like showing my work like this, like actually crossing out and saying it's going to be a negative 1 instead. So we would have negative 6i plus 8 times negative 1. And 8 times negative 1? Negative 8. And I put the real part first. So it should be negative 8 plus 6i. I'm sorry, minus 6i. My bad. Okay, that was the simple versions. Now we're going to go for the big ones. Oh, we thought this was easy. That means this is going to be fabulous. Okay, so we have these FOIL questions. Now for the amount of time we have left, I'm only going to do one of them. We're going to do number 8, which I believe is number 6 for you. Is that right? Okay, if you want to see another example, it's on the online notes, but we only really have time to go over one more. But y'all are going to help me out with this one. What should I be multiplying first? The 2 and the 5. So everybody draw their 2 and 5 arrow. And what is 2 times 5? Great. Done. Then we do the next one. What should we be multiplying next? 2 times 9i. Very good. Those are the outside things. So 2 times 9 is 18, and then we have an I next to it. We're going to deal with the 4 now because we have to do it in order. First, outside, now inside. Negative 4i times 5 is negative 20 with an I. And then the last thing I'm multiplying is the lasts in both of the parentheses. Negative 4 times 9 is negative 36 I squared, since they both have an I. Okay, pause. Did I lose anybody here?
I keep forgetting the square.
Yes, that's going to be a place that you forget every time. A hint is it probably ends with a square. Notice all the problems we've done, the very last thing you wrote down in the first step had a square on it. That's going to probably be there every time for this type of problem. Okay, now we're going to do 2 things at once. What 2 things are we going to do? Add those 2 things in the center. And what else? Make the I squared a negative 1. I heard it. Fabulous. Thank you. So the I squared is going to become negative 1. Okay, let's do both those things at the same time.
18 plus 20?
18 plus negative 20.
Negative 28?
Negative 38.
Ooh, one is positive, one is negative. We're going to end up subtracting these. 18 minus 20, or 18 plus negative 20. Negative 2 with an I next to it. Very good. And then we have negative 36 times negative 1. And I heard it already. If we're multiplying a negative times a negative at the back, makes that 36 positive. And since I know I'm dealing with complex numbers, I can't have 3 parts to a complex number. I'm going to add the 2 real parts together. The 10 and this 36 should be added together. What should we get as our final answer here? 46 minus 2i. With a real part of 46 and an imaginary part of negative 2. So So that's just arithmetic with complex numbers. We're adding or subtracting, we're multiplying. But the reason that we learn all of these things is because this is within the unit called solving quadratics. Now, these quadratics are going to have imaginary solutions. When we graph them, like I showed you at the beginning of class, you can't use a graph to solve because they're going to be looking like this, where they don't cross the x-intercept. So we have to know algebraically how to solve these for their imaginary solutions. I'm only going to do problem number 2 again for time's sake, so you have a really nice example and I can go slow. But if you want to see that first example there, it's on the notes. We're going to solve this by square roots. If you never got to the square root unit, be a sponge right now and figure this out. We want to isolate the x squared. If I want to get this x squared all the way by itself, what am I going to do on both sides?
You said if you want to get it by itself, distribute?
There's nothing to distribute. But I want that x squared to be the only thing on its side of the equal sign. What's there right now? Very good. There's a negative 10 next to it, so I have to add 10 to get it to go away. Okay, go away. Gone. Gone. We have negative 18 plus 10. What's negative 18 plus 10? Negative 8. Okay. If we take the square root of both sides, because that's the process of solving by square roots, the opposite of square is square root. But what I do to one side, I have to do to the other. And when you take the square root of a number, you add the plus or minus. Again, if this sounds absolutely new to you, that means we're behind a lesson. We need to go back and do the solving by square roots lesson. Okay. The square and the square root are going to cancel each other out, so I just have x left. And then I have plus or minus the square root of negative 8. Well, we need to reduce that radical because I notice that that radical has a negative in it. And thinking back to what we did at the very beginning of class, what does the negative pop out as? An I. So it's going to go right here, right in front of it. But we need to break down the number 8. How can I break down the number 8? 2 and 4. Can I break one of those numbers down?
Yes, 4.
4 can be 2 and 2. Okay, so I have a pair of 2's and a singleton 2. So I'm going to end up with x equal to plus or minus 2I square root of 2. That's the solution. The reason it doesn't show up on a graph is because it's an imaginary number. You can't use a graph to solve this one. These are the ones where you have to have algebraic skills to be able to solve it by square roots, or eventually the quadratic formula, which we're going to learn next time. Okay, if there was a part of this process where you're like, I never got to this lesson, we need to catch up. Because this has a whole lesson to it. So I can explain it again, or we can go back through that lesson. Again, if you wanted the examples that we switched because you need a little bit more examples, my notes are posted online like normal, so you can see those that worked out all the way through.